Today we will start with the new module that is, and as well as it is a new curve as well, right? This one can be called, actually we will call DP curves, but actually this curve was developed by two Spanish mathematicians, professor, right, Delgado and Pena, right? If I first of all, I have to remind you about there are three curves that we have already studied, starting from Bezier curve, right, according to Bonsai polynomials, and we also have sideball curve and one-ball curve, right? These two curves have the original curve that is a cubic ball curve, right, with four polynomials, four-ball polynomials, and sideball and one-ball, because they share the same polynomial from degree 2 and degree 3, specifically degree 3, right? So, but they will be different from degree 4, 5, and 6, and so on, right? So, the popularity of sideball and one-ball, because they will take, because their algorithms take less computational time when compared to Bezier curve calculation. So that is why one-ball and sideball are very popular, and and they will be used to develop many applications since then until now, year 2021. And this is why there was the idea that we should develop a new curve, right, in the year 2003, right? This curve was developed by two, I've just told you that, from Spanish mathematician, right? They are from the same university, right? Departamento de Matemática Aplica. Okay, they are the professor in Spain, right? Delgado and Pena. Because there is a tilde here, so we can call. We have to put Y and read it like that. Pen, yeah, because N tilde is equal to N and Y. Like Sonia, right? Sonia. Very interesting. Okay, so go back to 2003, right? Delgado and Pena were developed a new shape preserving representation, right? For a shape preserving representation means this curve must be NTP curve, right? And we'll talk about this later. And with the better result, that is with an evaluation algorithm. Evaluation algorithm means the recursive algorithm that will be used for calculate the curve, right? The point on the curve. Okay, with linear complexity, it means the efficiency of this recursive algorithm is big O n. So this is very, very interesting, because if you could remember for Bezier curve, right? If you want to calculate the point on Bezier curve, you need to calculate by using n square complexity. For side ball, because side ball employ the Bayesian curve computation as well, so big O will be n square as well. And for Wang ball, this one is very interesting and make Wang ball curve popular, because Wang ball can generate the curve by using big O n or linear time computation. So this is quite impressive. And but the cons for Wang ball curve, because Wang ball is not shape preserving. Wang ball curve does not possess a shape preserving representation. So because Wang ball is not an NTP curve, so that's why if we could find a new curve, a new polynomial that have the linear time complexity for the evaluation of the algorithm, that must be very interesting. So that's why in 2003, right, when this paper has been published, right, it is very, very popular and very famous by that time. Okay. Okay, so we have to start from Bayesian curve, right? Okay, maybe I will have to review a bit about Bayesian curve, right? If you start from Bayesian curve, you can have the convex combination of the Bonsai polynomial, and this one is per Bonsai polynomial, and Bonsai polynomial can be written in terms of the binomial coefficient. Right? This one is binomial coefficient, right? That is normal. And then multiplied by alpha j. Alpha j is actually is a point Bayesian control point. Okay. We type like this as an alpha. Maybe it will refer to represent the convexity or the convex combination of the Bayesian curve. Okay, and the idea of Bayesian curve is the inspiration for building the new curve, DP curve, like this one, because Bayesian curve can be represented in many forms. Like this one is one form, like in the polynomial form, or we can represent Bayesian curve in terms of the monomial form, polar form, or even for the recursive algorithm for Bayesian curve, right? The Delgado algorithm is also another form, right? But it can be written, it can be observed that the Delgado algorithm for any curve of Bonsai form, right, can be, this one can be expressed in the following product. Okay, so if this one gamma t is a Bayesian curve, right, and P0, P1, P2 until Pn are the Bayesian control points. So we can have the what we call these kinds of interpolation metrics. Interpolation metrics, right? That will represent the Bayesian curve, right? Instead of using this formula, we can start from, okay, in order to make you understand this easily, so I will change the color into the blue one. And then if I am considering Bayesian curve of degree 2, oh no, sorry, of degree 1 first, P0 and P1, right? So if I want to find a Bezier curve of degree 1, right, I can use this one, 1 minus t, oh sorry, 1 minus t, like this. Okay, this is the Bezier curve of degree 1. Okay, this will be, okay, this is the matrix multiplication, 1 minus t p0, 1 minus t p0 plus t p1. Do you still remember how to multiply, how to perform matrix multiplication? Do you still remember? ยังจำได้อยู่ไหมคะกัน2 คนตอบแล้ว Okay, yes. And Minคะ Okay, thank you very much. Because I want to make sure that you all can follow my words. Okay, so this one is the degree 1. Okay, and for the degree 2, right, degree 2 we will use this one and this one. Okay, and multiply by p0, p1 and p2. Okay, and this one is the general formula. Okay, this will be the general formula, generic formula. So if you have the formula like this, you may have to, okay, gamma t is equal to 1 minus t. Okay, I have to write this first, and then I have to multiply 2 matrix here, right? 1 minus t, it will be 1 minus t p0 plus t p1. Actually, you have to plus 0 multiplied by p2, right? But we don't have to write it because it will be eliminated because it is a 0. And then go to the next step, 0 p0, 1 minus t p1, 1 minus t p1 plus tp2. So this is the result for the last 2 matrix multiplication, these 2 matrix multiplication. Okay, and then we have to go on with that and by multiply these 2 matrix together, and then you will have, okay, gamma t is equal to this one and this one and this one and this one. Okay, so we have 1 minus t multiplied by the upper one, 1 minus t p0 t p1. Okay, I have to use this one, this square bracket, and then t, once again 1 minus t p1 plus t p2. Okay, that's all. And when you expand or simplify this term, you will get the quadratic Bezier curve. And you can do the same thing with degree 3, 4, 5, 6, and so on, right? So you can get also the same equation for your Bezier curve. Okay. So what, how can we generate this matrix? How can we generate this matrix? Okay, I will, okay, have you finished writing this one? So I will clear this screen. Okay, in order to generate this, so we have to start from 1 minus t and t, right? This one is for the matrix 1 by 2, and this one will be 2 by 3, and then 3 by 3, no, sorry, 3 by 4, and then 4 by 5 until n minus 1 n, something like this, right? This is the way that we will generate the matrix list, the sequence of the matrix. We will start from 1 minus t and t, and then for the next matrix we will have 1 minus t and t, but we have to shift one column, and then we will write down 1 minus t and t, and so on. We can do this step like this until you can get the metric that is related or corresponding to the control point here. So the last matrix will be 1 minus t t, 1 minus t t, 1 minus t t, and so on until you can get 1 minus t and t like this t, right? So this will be from 0 to n, right? This one is from 0 to n minus 1. No, I think it's not. I think this one is 1 minus 1 and this one is n. So 0 to n and this one is 0 to n minus 1. Up to this, do you have any question? ถึงตรงนี้มีคำถามไหม Formulate matrix นี้ได้ไหมคะ Can you formulate this matrix? Okay. In order to make sure that you can generate this matrix, right? I will later on you can try to write the mathematical program in order to prove this. I think you have seen this kind of formula from the previous slide, okay, last week, right? You have seen this kinds of the matrix, right? This and the original idea of doing this was found in this paper. Okay, we start from the Bayesian curve, and then we'll go to the formula for the polynomial, the new polynomials by Delgado and Pena work, right? They start from the generic idea of polynomial constructing by let C0, C1, C2, C3 until CMM, right? When m is greater than or equal to 0, we'll form the system of polynomial on T is in the range of 0 to 1. And they can be divided by, okay, C0 is equal to 1 minus T raised to the power M. And Ci will be T multiplied by 1 minus T M raised to the 1 minus T raised to the power M minus I, right? And this one is from I from 1 to half, right? And from another half to M minus 1 will be used, you will use this one. And the last polynomial, right, will be CMM, will be equal to T raised to the power M. And if for the case M is even, so you have to add one more polynomial in the middle, which is this. This is one more polynomial in the middle when I is equal to M divided by 2. This is even. Okay, but M is odd. You will have to, okay, you have to have a special one, right? Special two polynomials in between. Okay, this in the middle. This is two polynomial in the middle. Okay, in order to get this form, right, Delgado and Pena did very easy. They start from the previous idea that I have just told you, that is about this one, right? This matrix, right? And then he come up with this matrix. Okay, So for the Delgado and Pena, right? For the case for degree 1 minus t. Degree 2 still it is still the same as Bezier curve, right? 1 minus t and 1 minus t. Okay, that's okay. But for degree 3, right? It's not the same as Bezier curve. It is 1 minus t and 2 middle coefficient will be half 1 over 2 or 1 second, and then 1 minus t and t. Okay, it was very funny that in there were a few papers that refer to later on the 2003, right? They were trying to refer to this curve, and they thought that okay, ใส่ ball หวัง ball, so this one we have to call it DP ball, because they didn't know that the reason why we call ball curve, we call ใส่ ball curve and หวัง ball curve because the curve, two curves share what? Share degree 3, right? Cubic ball curve. They start from the original cubic ball curve, right? So that's why side ball and wang ball can be called side ball and wang ball curve. But for DP curve, right? Because wang ball, this term is not 1 over 2, for sure. So we cannot call DP ball curve, right? Okay, so when I know this, right, I write a paper in order to claim that you have to call DP curve. Okay, and from that time, right, when my paper was published, right, everyone will call DP instead of calling DP ball curve, they will call DP curve. Okay, this is the history. Okay, so in the next step, right, degree 3, this one is degree 2, and this one is degree 1. How about degree 4? It will be 1 minus t, 1 minus t, but it will be 1 and 1. Very simple. And then when degree 5, it will be 1 and 1. But in the middle, we will have 1 over 2 and 1 over 2. So you can see that Delgado and Pena curve is very simple. It's very simple in the sense that they don't have to calculate for the coefficient. Actually they have to, but if you consider the matrix representation, right, you don't have to calculate for this one because it's 1 alone or 1 over 2. Okay, this is the simplicity of using Delgado and Pena curve or DP curve. Okay, so you know that, and when they find this formula, so you have Delgado and Pena will have to formulate the equation of the polynomials of its curve of their curve, so they can get this formula. I would say that it takes time. It took time, okay, in order to convert from this one and this one. And also, like for me, right, when I saw this paper for the first time, so I have the idea that I would like to have my own curve or my own series of polynomials that will come true, okay, and okay, because of using this technique, right, so you can find this polynomial. And I have to say that when you find this polynomial, right, you cannot just use the polynomial by yourself alone, right? But your polynomial has, the equation of your polynomial have to satisfy the first one, linear. If you could remember, linear combination and affine combination, and the last one is convex combination, right? Because we want to prove this one, this sort of actually we have to prove this one, right? Whether this one they satisfy this property. Why do we have to check whether DP curve is a convex combination? Why ทำไมเราถึงต้องเช็คว่ามันเป็น convex combination คะซึ่งเป็น convex combination ก็ต้องเป็น affine combination ด้วยเนาะ Why and how มิ้นท์คะตอบได้ไหมตอบให้ครูชื่นใจหน่อยสิ ว่าเรายังรักกันอยู่มิ้นบอกหนูไม่รักอาจารย์ละค่ะมาถามลูกหนูเนี่ยวันนี้กำลังง่วงๆอยู่ด้วย After you a few times, that's why we have to okay, we have to start our course by convex combination, right? If you could remember the first week, right? We have to prove for the convex combination. And I've told you that time, right? Why do we have to use, or we have to prove for the convex combination? And later on in Bezier curve, right? We also talk about this as well. And also for cubic ball curve as well, right? We have talked about the proof of the convex combination. I've told you that. Why do we have to make it convex combination? Bob คะตอบได้ไหม Can you answer this question? เงียบทั้งคู่เลย
It should in the how is it in the square or in the it means it should be in the convex hole. Convex
hole.
Yes.
If you can prove that the formula is a convex combination, so it can be proven that the curve
including in the convex hole. Yeah.
The curve line, okay. The curve lines inside the convex hull of what? Of the control point. Okay, that's good. Thank you very much, Bob. That's correct, right? Because we want to prove this, because the reason why, suppose you want to write a program or software or CAD application, and then when you mark the control point on the screen in order to reference the control point of the curve, right? And if you draw like this, but the curve is outside the shape that you have defined, or it's out of the boundary of the convex hull, that would be nothing, right? But it would be better if you can frame the curve inside this one. And we can call this including the boundary of the control point as well, right? We can call this polygon the convex hull of the control point. And the curve can be divided inside of this convex polygon. Okay, or we can call the convex Hall of the control point. So how can we check for the Delgado-Pena curve, whether it is a convex combination or not? How can we do? So what you have to do is, first of all, you have to write the program in order to show all polynomials, right? All DP polynomials. And then for affine combination, the second choice, right? You have to check whether the summation of all polynomial, right? Which is CMIT, right? Can sum to 1. Right, sum to 1, right? And then for convex combination, you can just simply prove that for each C, right? CMIT, right? They are greater than or equal to 0. But this one is easier to prove, right? You can just simply like try to write down the, have I shown you the technique of Bonsai polynomial, right? The Bonsai polynomial can be plotted into the graph like this. Can you remember? Right, and I say that this one is from 0 to 1 and 0 to 1, right? This forms the range 0 to 1, right? Okay, and nothing. I mean, the curve cannot be below the x-axis, so we can prove that the polynomial p in, okay, this form p3i, right? BTIT is greater than or equal to 0 all the time, right? Because this curve is above x-axis. This one is also above x-axis. This one also. This is a curve of the Bonsai polynomial. So if we can prove that the p polynomials, we will have the curve only in this region from 0 to 1 and from 0 to 1 here, right? If we can prove that, or if we can plot that, so we can prove that the DP curve is okay, not actually convex, just only this one, this property is correct. But we also have to prove the summation of them, right? If we can prove that summation of them is equal to 1, so we can conclude that it is convex combination. Okay, now I'm not going to prove this, but maybe you can write a program later on. I have to lecture you first, and then in the laboratory, maybe you can try to prove this one. Okay, by writing the DP polynomials and then try to prove for the convex combination for all of possible n number, right? And this one is the way that we will evaluate the algorithm for the DP curve, right? By using the what we call the recursive function. Okay, once again, if you could remember 1996, right? If you could remember the recursive formula for Said ball and Wang ball, right? It was written in terms of like this. If you can remember this, right? This one is a recursive form that is very similar to the recursive form of the Said and Wang ball in 1996, right? Also in this paper, they adopt the technique of right, in order to represent the recursive formula for the DP curve as well, right? And okay, it's very simple like this. Okay, but they also there are also the odd and even degree, right? That's not what we call the elegant things, right? And then you have to separate into 3 parts as well. If you compare to my formula for the recursive algorithm for side one ball, right? There are only 3 or 4 Line of code, lines of code, right? That is very simple, right? Compared to this one, this formula. Okay. And then come back. Okay, this is a recursive algorithm that provided in this paper. Okay, and then we come back to this, right? This one is the way, sometimes we can call it is a interpolation matrix. Interpolation matrix. Why do we call it interpolation matrix, right? If you could remember, this one is the interpolation equation, right? If we have 2 points, P0 and P1, right? If you want to draw, or if you want to get all points in between P0 and P1, right? According to from 0 to n, right? We can use this formula 1 minus t P0 plus t P1, right? This one can be proven by physics, or can be proven by linear algebra, right? When it is given P0 and P1, right? We can plot the point on this line, okay? Starting from P1 or P0 and P1 to P1, right? This we call interpolation, right? And from this one is also interpolation. And this one is also interpolation matrix as well, because 1/2 P0 plus 1/2 P1 is also the interpolation as well, right? Once again, I have to remark here that the coefficient that is a that multiplied by P0 or P1, right? When we sum of them, we can get 1. 1 minus t plus t is equal to 1, right? Okay. 1 second plus 1 second. Okay, 1/2, right? We can call 1 second, right? This one is 1 second. This one is 1 second, 1/3, 1/4, right? This 1 second. Okay. 1 second plus 1 second is also equal to 1. Okay, so this is a trick, right? Every line, sorry, what's happening? I have to come back to here. Okay, come back to this this slide, right? So this is a trick, right? This one will be when you add all coefficient here, you will get 1. If you add 1 second plus 1 second is also 1, right? If you can see that this line, the summation will be 1, right? Even we have just only 0 and 1, right? Sum to 1. So this is a trick. And this trick can make the system of polynomial to be convex combination. If you use this trick, right, every line can sum to 1. This one will generate the convex combination polynomial. I cannot prove this, but it's from the experiences. Okay, it will form and if you can get the convex combination polynomials, right, you can also, if you can remember, you can get the monomial, right? And for monomial, right, it is inversible. Sorry, I have to say inversible. Inversible means you can find inverse. Invertible. Okay, invertible. Can find inverse. invertible คือสามารถหาส่วนกลับได้หา metric inverse ได้ okay and this is not an accident, right? This formula is exactly the same as this figure, this right hand side figure. Okay, if you can see that this one is V5, right? We can use 1, 2, 3, 4, 5. I love you. No, just kidding. Okay, this is degree 5, right? If you want to reduce degree 5, right? Because you want to find a point on the curve, right? You have to reduce from degree 5 into degree 4. In order to get that, you have to multiply the control point by this, right? And this one is V4 and this one is V1, right? V5 you can get 1 minus TT. This one 1 minus TT. If you could remember, this is V0 and this V1, right? This one is 1 minus T V0, 1 minus T V0, and 1 and plus T V1. 1 minus T here. เห็นไหมทันไหมลบอีกอะ considering this 1 minus TT, this will be multiplied by V0 and V1. V0 is here, V1 is here. Linear interpolation, 1 minus T V0 plus T V1 is from this one and this one, because this will be multiplied by V0 V1, right? Okay, and then this one is linear interpolation, half ครึ่งหนึ่งหาครึ่งหนึ่ง this one is a linear interpolation. It's exactly the same as this formula. And also this one is 1 minus T and T. This one is 1 minus T and T. Okay, I use the red control point, which will represent the new one, the new control point after interpolation. Okay, and then the next step is 1. This one refer to the third control point, that is V2. So V2 will be the same place. If this is 1, right? 1 multiplied by V2. So V2 is exactly the same location. Now it will be V1, V prime 1. This one is V prime 0. This is a not prime, V caret, right? V caret or V prime, okay? That will refer to the next step of V, right? We are going to change the control point from degree 5 into degree 4. And then this one is also 1. That's why this one will be this point. And 1 over 2 and 1 over 2 will be this point. 1 over 2. This one is 1 over 2 of V2 plus 1 over 2 of V3. Okay, this one V2 and V3, right? Okay, this is the way, sometimes we call this as a corner cutting algorithm. The reason why we call corner cutting algorithm is because it is a corner cutting algorithm, right? The corner will be disappeared all the way. It's like you chop an apple, right? Until you get the shape that you want. Okay, and then we can do this one. Okay, for the first step, you can get degree 4, right? Like the red one, right? Now the control point will be smaller. And then we can do this, right? According to the next step, this matrix, right? So it will be like this and like this, right? And then and then we can get this one and this one. Until we can get the final result, which is this point. This point will, according to t is equal to 0.5. This is the way that this one does, and it can be represented in terms of the figure like this, like an interpolation figure. เป็นภาพการ interpolation กัน Okay, this is a key point in this paper, right? To get the Delgado-Pena polynomials, and okay, we can go to see this paper. I'm not sure whether I give this paper to you or not. Okay, before we go to Jiang and Wang, right? I have to give you the paper. I have to give you the paper, right?อยู่ไหนเนี่ยโอเคครูให้ไปแล้วนี่ you can see Delgado-Pena 2003, right, in this PR. Okay, let me show you the paper. Okay, you can see this paper, right, 2003, right, and then you can see this paper from introduction and introduction, right, because they want to show that the NTP, because in the past, right, when Goodman and Said, right, they try to claim that if a curve has the shape preserving property, the curve will have normalized totally positive or NTP basis. The basis is equal to polynomial, but polynomial is general form. But if you can find the polynomial, right, which has the concept of the convex combination, or the matrix, the coefficient matrix can be invertible, right? We can call this basis. Do you understand what I mean? Polynomial ก็เป็นทั่วๆไปอะค่ะเวลาคุณเอาไปทำเป็น matrix มันก็จะเป็น matrix ใดๆแต่เราไม่สามารถบอกว่า matrix ใดๆนั้นมันจะหา inverse ได้ถูกไหมมันไม่ใช่ว่า matrix ใดๆหา inverse ได้แต่ถ้าเมื่อไหร่ก็ตาม matrix ใดๆอันนั้นมันเป็น convex combination แบบนี้เผอิญมันจะหา inverse ได้แล้วพอมันหา inverse ได้ปุ๊บมันก็ convert จาก basis หนึ่งไป basis หนึ่งได้นั่นคือว่าทำไมถึงเรียกว่า basis. Okay, I explain in English. Okay, normally when you have the set of polynomials, right, and then you can convert the polynomials, right, according to the control point into the matrix form, right, and that matrix form, if you found that, or if you can prove that it is a convex combination, we can call that this one is the linear independent. What is the property of the linear independent? It can form a basis. A basis is a special kind of the polynomial that if you convert into a matrix, the matrix can be, you can find the inverse of the matrix. And we can call this kinds of polynomial basis. Okay, And if you want to make sure that curve, your new curve or your new sequence of polynomial and can form the curve, or if you want to prove that this one is the shape preserving property, you need to prove for the NTP basis. And this is a long story. You have to find the whole location matrix and so on, right? But I'm going to say that when in 2006 or 2007, right, I tried to ภาษาไทยเรียกหักล้างอะ I try to object this system เปรี้ยวไหม เวลาสอนครูไม่อยากสอนเรื่องนี้เลยเพราะสอนแล้วครูเหมือนนางมาลายยังไงก็ไม่รู้อะเดี๋ยวดูแล้วกัน นะ I refuse to follow this idea because when I prove this, okay, side ball is a NTP basis, but wang ball is not NTP basis, right? So they prove that wang ball is not shape preserving, but side ball is shape preserving. But I try to refuse this conclusion because even DP curve is shape preserving, following by NTP basis, but it's not shape preserving. Actually, okay, I'll tell you later why I call that, right? And this one is the definition of the DP curve, right? I have told you already. And then the idea is starting from the Bonsai basis like this, and then they try to solve, or they try to make it to be a new system of polynomial. And then this one you have already seen it. And then this one is a recursive formula that you can use for calculating the points on the DP curve, right? And then for the second section, right, they have to put for the totally positive of the basis and so on, right? And I say that is useless. Sorry, it's not shape preserving, okay? And so on, right? They try to prove this one because they want to claim that this one is new and very useful, right? According to the linear, the most interesting property of the DP curve is the recursive formula here. The recursive formula here, right? That they have a remark here, and then for the case of M is odd. I'm sorry, I didn't put this into the lecture slide, but this one is very important because M is odd, then the number of sum is 2M, and multiplication is 4M, right? You can see this one is linear, right? 4M. And for even case, right, the number of sum is 2M minus 1, and for multiplication is 4M minus 2. So this one is also linear. Okay, that's why we can call this formula or this curve possesses linear time computation. Or we can say big O is N. Big O is N. This is the best thing in this paper. This is the best thing. If they cannot claim that this one is, this recursive formula is linear time computation, this paper will be nothing. But at least I have to respect to the way that in this paper is the inspiration of me and my students to come up with the new basis or the new polynomials, not only for the univariate polynomials, but also the bivariate polynomials that for the curve modeling and the surface modeling. Okay, if you have time, you can go to the surface modeling and you can see the bivariate polynomial. Okay, that's all for this paper. I'm going to skip into the next one. stop share, and then we'll go back to the next next paper. Okay, this one is a DP curve. Not actually, because this paper was developed by Chinese professor and his PhD student, Zhu Longjiang. Zhu Longjiang is I think he was a PhD student by that time, right? And in China, in Hangzhou, right? Together with the professor Wang Gujin. Wang Gujin is not the professor who developed the Wang ball, right? Sorry, not Wang Gujin, Wang Guchao. Actually, Wang Guchao. But there are many papers about Wang ball curve or Wang ball surface that were developed or that were invented by Professor Wang Gujin. Okay, this paper we try to show the conversion. Okay, once we have the curve, right? So the most important property that you have to know that is you have to convert from one basis into another basis, or one curve to another, or Bezier curve to Wang ball curve. Or in this case, we can find that DP curve has a linear time complexity. So what you have to do is you have to find a formula in order to convert from Bezier curve into DP, right? Bezier has big O(n) square, right? But DP has big O(n). So we have to convert from Bezier curve, right? One time, right? Into DP control point, right? And then using big O(n), right, computation, we can find the curve, right? So we want to print the Bezier curve, right? So instead of using the Delgado-Pena algorithm, which has the quadratic time computation, so we use DP control point, just convert this one time. And then in order to calculate for the point along this curve, right, of the same curve, right, you may have to calculate for maybe, if you want to get the smooth curve, you may have to calculate for 4 or 500 points. So this one is very a long series. So you have to, it's better to convert into the DP control points and then use big O(n) 500 times. Okay, in order to generate for the points on the curve to make a smooth curve. So that's why we need to find this relation or this conversion. So this conversion will be found in this paper, right? 2 years later. Okay. We will start from the DP ball basis. Just, you know, this now we call this basis. And this is funny. DP ball, hello? No, you cannot call DP ball. Okay. And then this is the formula, the conversion formula, right? First of all, you may have to find this 3K, K1, K2, and KT, right? It can be written in terms of this formula. I'm not going into detail about this because it's going to be okay to be used later on, right? In this formula, you can see that this is a theorem in this paper. Let's see, will be DP ball basis and B will be Bonsai basis. And then you want to convert from Bezier to this. To convert from one basis to another, you can use this conversion matrix E, big E, right? And big E, we have the element small e, Eij, right? Eij is an element in the square matrix. This one is a square matrix, right? N plus 1 by N plus 1, right? This will refer to the Bezier curve. or the DP curve of the same shape, right, with degree n, but n plus 1 by n plus 1 matrix. Okay, and you can calculate for EIJ. EIJ is each element in this conversion matrix. Okay, and then, okay, you can have this for even case and this for odd case, right? And you can use this formula, right? The formula is very complex, right? So that's why we have to divide into K1, K2, and KT. This one is K1. We also have K2 and KT. If you see this formula, conversion formula, what do you think about this formula? If I ask you to write a program in order to calculate for this formula, what should we do? Oh my God, it's too long, right? It's very complicated, and I'm not sure whether it will be correct or not, right? So, and also in that paper, it's not correct. There are some mistakes in that paper. So that's why in 2010, right? 5 years later, I try to object that paper, right? I like the paper related to this paper, right? We will go to see inside this paper. The first thing is that the formula is not correct. Okay, maybe I have to stop. Okay, I propose the new conversion matrix from DP curve into Bezier curve. DP curve into Bezier curve, okay? Why? Because this one is the control point for DP curve, right? We want to convert into Bezier curve. But in the real world application, you need to convert from Bezier curve to DP curve. Okay, I will show you the formula later. This one is a formula, right? And then formula is quite long, right? In order to get this theorem 1, right, in this paper, right, I use the polar form approach in order to prove for the conversion from DP curve into Bezier curve, right, and I come up with the formula, right. This is a general form, right, and if the curve is even degree, right, you can follow this formula, and if the curve is odd degree, so you can follow this one, right. It's a bit complicated, but it's also better than the previous one that provide in this one, right, which is a bit more, it's simpler. Okay, but I think this one is not enough for me, right. I also try to convert this into the monomial form, right, like this. If you can always heard that I always say that, because I'm not going to use polar form anymore, because this one is complicated and very difficult to prove, right? But instead of using this, I use the monomial form, and I try to convert everything into monomial form. For this case as well, right? Because we can convert from from DP curve into Bezier curve using this matrix, right? But we also have the conversion inverse matrix as well. If we want to convert from this one, I change the color from blue to from red to blue, right? If I want to convert from Bezier to DP, right? I can just simply use CN inverse. I can use the inverse matrix of this matrix. Am I right? CN inverse, right? Because I have told you that I can prove that DP curve, right? This matrix is basis, from the basis. And then this one is the linearly independent. Linearly, if you could remember this word linearly, linear independent. If you can prove that it is a linear independent, you can say that this one is a basis. This one is in linear algebra. But in CAGD, like if you can prove that it is a convex combination, you can also prove that this is our basis function as well. Okay, so we will have a very shorter, very elegant way to find Cij. What does it mean by Cij? Cij is each element inside this matrix, right? And it can be calculated by this formula. Very simple. So if you want to find the conversion from DP curve into Bezier curve, right, I suggest you to use this matrix. Find this matrix and then calculate for the inverse matrix. Inverse matrix here. Okay, this is the conversion from DP into Bonsai basis or Bezier basis. Okay, this is a paper นางมันบายเนอะบอกว่าของเขาผิดเนาะแต่ครูก็เพิ่งค้นพบว่าจริงๆแล้วเนี่ยการที่เราเป็นสายดาร์กมันก็สนุกดีเนาะไปหาว่าคนอื่นเขาทำผิดอะไรแล้วเราก็มาแก้เปเปอร์แล้วก็ได้ตีพิมพ์ด้วยOkay, up to now, do you have any questions? มีคำถามอะไรไหมถ้าไม่มีก็จะไปต่อนะกำลังเพลินเลยใช่ไหม Okay, this one is the next paper, right? But it is for the surface, right? In order to construct for the triangular DP surface, right? We can use this paper. Okay, go back to 2008, right? Why do I have to represent to show you this one, right? Because this one propose a new DP polynomial, right? This paper combine odd and even case into one case, right? If you can see for the left-hand side of the screen, you can see that the original DP polynomials, there are two cases, like even and odd case, right? And in the right-hand side, you can see that this one is combine the even and odd cases into the same formula, right? Even it is quite long, but it seems to be better, right? And I also use this formula in order to use the polar form approach in order to find the conversion from Bezier to Wang-Ball and Wang-Ball to Bezier. Okay, and so we can prove that DP basis, right, is the positivity. This one is proof for the convex, right? It's greater than or equal to 0, right? And normality is the summation is equal to 1. Sum to 1. And symmetric CNI 1 minus T is equal to CN but N minus I and T สมมาตร and recursiveness, you can write the you can write the polynomial in terms of the recursion. It can be written in terms of its recursive formula. เรียกตัวเอง Okay. Okay, we have already studied about, okay, first of all, you know about DP curve, right? And the DP curve, right, we have all the different cases, we combine them in 2008, right? And then we use that in order to find the conversion from Bezier to DP, right? And we also prove that DP is also the form of basis as well, right? And then, okay, we have known about the the recursive algorithm for DP, right? So what will be left for the curve properties? The next curve property that you may have to know that is a multiple degree elevation. If you could remember, right? Also, this is the work by me and my PhD student, okay, Shannon, right, by that time, right? And this one is submit to computer and mathematics with application, or we can call CAMWA, right? This is also a quartile 1 paper. Oh, sorry, quartile 1 journal paper, right? Also the previous, I'm not sure previous. This one is also CAMWA or AMK. Okay, CAMWA as well, quartile 1. Okay, this one is to find the multiple degree elevation by using monomial basis, right? So this is the first time that DP monomial basis has been published, right? Instead of using only DP polynomial, right? I and Shannon also represent or present the Dij, which is an element in the monomial matrix, right? And then we provide also the proof of it. And then, no, just in this paper, we just show the formula, but in 2013, right, I and Delgado, right, show the monomial form of the DP and it's proof, right? You can prove the DP monomial like this. Okay. And this one is multiple degree elevation, right? By using use the extended DP monomial matrix, right? By add k columns, right? If you want to find the k times, right? Degree elevation for k time, you can add k column. But if you maybe 1 0 0 2 3, okay, I will just give you an example of the DP monomial matrix, right? And then I just simply add up 0 0 0 to this, right? So I can find I can call this one is extended DP monomial matrix. If I want to find only one single degree elevation, I can just add 1 column. If I want to do 2 degree elevation, so I add 2 more, right? But this time I want to find just only degree elevation, so I just add 1 column, and then I can get the degree elevation for DP curve. But in this paper, I want to make it general, so I try to show the multiple degree elevation for DP curve of any degree elevation. So it would be very, very, because in order to publish in a journal paper, right, you need to compact your paper. When I wrote this paper, oh my god, it's about 20-30 pages of this paper. But when I submit to this journal, they try to chop the number of the pages into just only 4 or 5 pages to be published, can be published in this journal. Okay, maybe just 4, pages. Okay, that's why you can see that the theorem proposition is very short, and there are no examples, right? Because they want to save the page. Okay, and also in this paper, I also provide not just only the decay elevation, but also the decay reduction as well, right? If you want to find the decay reduction, right, you can just simply use this theorem and this proposition in order to find the decay reduction. Right, this one is a theorem and proposition for finding the decay elevation for DP. And that would be all of today's class about DP curve.